Hello, good evening to everyone. Welcome you all to the live session 6 on the course Manufacturing Process Technology First and Second. In this session, we will try to solve some examples based on the video lectures of the week 6. So, let's get started. So, this is the first question. Please read it first, try it by yourself, and after that, we will discuss it together. So you can keep your response in the chat box.
Hey,
Hello, we are
Martin.
solving the problem number 1. You can give your response in the chat box. Okay, I have got response from Nishu. Others? Okay. Yes, I think all of you are correct. So let's quickly try to see what has been asked in the problem. So here if we see in the question, so the secondary deformation zone in metal cutting operation is located around, and these are the some of the options which is given. So let's try to quickly see the schematic of the cutting process. So again, here we have a tool. Here we have tool, and the blue one is the workpiece, and cutting process is happening. How it will happen? So cutting process will occur only if there is a relative motion between tool and chip. So uh, so let so let's say that our workpiece is moving from the velocity v towards the right side, and our tool is fixed. So the cutting process occur because of interaction of the tool tip and the workpiece material. And why it is happening? Because our tool is applying a compressive load to the workpiece, and because of which a small layer of material which is here, we call it uncut chip thickness or T1. This much layer of material is being removed, and this is the shear plane. This is the shear plane along which deformation is happening. So because of this workpiece and tool interaction, there is several there are three zones which we have identified. So based on the what happens because of the tool and workpiece interactions, uh, different kind of deformations takes place, as well as temperature rise takes place. And in different zones, uh, different amount of temperature rise takes place. So out of which this is this zone here, the majority of deformation takes place, and this is the main zone which is responsible for the formation of the chips or shear deformation of the workpiece material, and this is called primary deformation zone. So the primary deformation zone is primarily because of the shear deformation happening inside the material. But apart from primary deformation, there are other deformations also takes place during the process of cutting. So another one is sorry, another one is the secondary deformation which takes place here. And why deformation takes place here? Deformation in secondary region happens because the workpiece material which keeps on coming like this, after the after getting sheared, they change it changes direction, something like this. And since now the velocity of chip, our chip has some velocity called vc. Now our workpiece material which is sheared off, it is moving with a velocity vc, and our tool is fixed. So if we see this surface, this is called rake face. So there is a relative motion between the chip and the rake face. Also, our chip is applying some normal load on the tool, as well as there is a reaction force from the tool on the chip, and there is a some friction coefficient of friction between the chip material and the tool material. So if there is a relative motion and there is a normal force and there is a friction coefficient between the chip and tool interface, the friction force will also act on the tool surface as well as on the chip. And because of this friction force, okay, I will because of the friction force, the material which is near to the which is very close to the rake surface of the tool, it it will get it will get deformed again. So this deformation zone is created because of the frictional force between tool, rake face and chip, and this is called the secondary deformation zone. And there is also another tertiary deformation zone which happens here. So what happens? Some part of the workpiece, some part of the workpiece, it comes with the contact of the while after cutting operation. Ideally, what should happen? Ideally, the whatever material coming here, it should not get disturbed and it should keep on moving without any disturbance. But in reality, what happens? Some portion of material also interacts with the, this is called a flank. This is the flank of the tool. Some portion of the metal very close to the tool tip comes in the contact of the this surface, flank surface, and because of the rubbing between the flank surface and the uh, material and the workpiece material which is moving away, there is a small deformation zone created very near to the tool tip, and this is called the tertiary deformation zone. And in all these regions, temperature rise takes place. So for this question, the correct answer is the secondary deformation zone which is here. Secondary deformation zone is nothing at the tool chip interface. So already you have given correct answer. So if still there is any doubt, you can ask me. Otherwise, we will move to the next problem. Okay, we will move to the next problem. Please read the problem and you can give your response in the chat box. After that, we will discuss it together. I am waiting for everyone to respond in the chat box. After that, we will discuss it together. Okay, let me try to help you out. So, what has been asked in the question? Temperature rise in primary and secondary deformation zone is generally due to. So, in the previous problem, we have identified what are the primary deformation zone, secondary deformation zone, and tertiary deformation zone. Okay, Hamid, I got a response. We will try to see it and we'll try to discuss whether which is the correct answer. Okay. So again, let's start looking at the same schematic. So again, here this is the workpiece or the job here, job or workpiece, and here we have tool, and let's again we can try to identify what is the primary deformation zone, well just secondary deformation zone. So we can see here now the we have rotated the diagram. Right now what is happening, the workpiece is moving with a velocity vc towards the downwards, and we can assume the tool is fixed. So there is a relative velocity between the workpiece and tool, which is vc, and again we can identify the faces. So this is the chip we know, and this is the rake face, and here it is flank. So this is the flank of the tool. So, if you remember from the previous question, so the primary deformation zone was the it is the shear zone, or the where the shear is taking place. So this zone we can see, this is what, this is nothing but shear plane, and the zone surrounding the shear plane, it is the primary deformation zone. And here, this zone, this is the reason where the chip and the rake face of the tool is coming in the contact. So it is the secondary deformation zone. And the last one here, the flank and the workpiece. So this is the tertiary deformation zone. So here in this case also we have identified all the zones, but here I have shown some arrows, out of which you can find one arrow has bigger size and one arrow has smaller size. So if you see for the primary deformation zone, here we have drawn arrow here something like this. So here, so the bigger arrow is pointing towards the chip and smaller arrow is pointing towards the workpiece. So it is just to it signifies that the whatever the heat has been generated in the primary shear zone, so the majority of heat is carried away by chips, and a minor portion of the heat is retained within the workpiece. And similarly, if we try to see the distribution of heat in the secondary deformation zone, we can see the bigger arrow is pointing towards the chip and smaller arrow is towards the tool. So in secondary deformation zone also, the majority of heat is again taken away by chips, and only a minor portion of heat get transferred to the tool. So why it is like that? So basically, most of the time the workpiece material is metallic, it has high thermal conductivity, whereas the tool has relatively poor thermal conductivity. So whatever heat is gets generated, it gets quickly transferred inside the uh, chip, so which is metal. Therefore, the majority of heat is going inside the chip. And why do you think there is in this? Let's say if we talk about the primary deformation zone, if deformation is happening, why the heat is getting generated? Can you think of a reason why heat is getting generated in deformation zones? So it may be tertiary deformation zone also. So wherever plastic deformation is taking place, heat generation is happening. So what can be the fundamental cause for that? So Technically, if you see, we are applying some force on the tool, and we are getting some reaction force from the workpiece. And how this force is getting transmitted, gets convert it's how the force which we are applying is generating the heat. Anyone? Okay. Okay, so fundamentally, if you try to answer this question, so what is happening? So why deformation is happening? So it is happening because of the uh, breaking of bonds, or because of dislocations movement. So the fundamental cause for heat generation is the energy which we are supplying. So that is going to break the bonds, and that energy is going to get converted into the heat. So whatever the extra energies remains after breaking the bond, that is going to convert it into the heat. And if you see the right side of the this figure, so what is it's showing? It's showing it is showing that at different cutting velocities, what is the fraction of heat which is being carried away by chip, tool, and blank or the workpiece. So what we can conclude from this figure? This we can conclude that whatever the heat is going generated in either of the deformation zone, like primary deformation zone, secondary deformation zone, tertiary deformation zone, so that is the majority portion of that heat is taken away by the chips. And in fact, that is good for us, because whatever chip is getting generated, we are going to throw it off. So it is good that majority of heat which is getting generated, it is getting automatically taken away by the chip, because the heat which is getting generated, it is it has different detrimental effects on the tool as well as the workpiece. So if you try to note it down, some of the effects of the heat on the tool and the workpiece, so I would like to write it point wise. So let me add some slide. So actually I am teaching this because it is important to know, means if if uh, if temperature rises more because of generation of heat, then what will be its effect on the tool as well as the workpiece, because we are doing machining to get the final component which should have accurate dimensions as well as good surface finish, and it should be economical, and uh, as well as we want good tool life. So if heat generation will be very high, then what are the effects? So I am noting it down. First I will write the uh, effects of the temperature on the tool. Effects of high cutting temperature on tool. So first one is the, if temperature is very high, then tool wear happens rapidly, and that is not economical for us. So we want tool wear to happen slowly, or we can say we want longer tool life. So first detrimental effect is rapid tool wear. Secondly, if temperature rises too high and our tool doesn't have very good high hot hardness, then what will happen? Its cutting its cutting edges gets plastically deformed and our tool will become blunt. So what will happen if our tool will become blunt? We need to apply higher force to cut the material. So our cutting process will become difficult. So second detrimental effect is plastic deformation of the tool edge. Of cutting edges of tool. And the next one is sometimes uh, because of the thermal shock, rapid rise in temperature and then rapidly cooling it down, there is a fracture takes place on the cutting edges of the tool because of the thermal shock. So that is also our tool gets damaged. So thermal cracking of tool, cutting edges of tool. And one more effect uh, which adversely affects the tool life, that is called built up edge formation. We will discuss more about this built up edge in uh, in next questions. So I will skip it here. So we will discuss it more thoroughly in the next question. And now I will note it down some detrimental effects of temperature rise on the workpiece. Detrimental effects of cutting temperature on the job or the workpiece. On the job. So first one is the dimensional inaccuracy. So how this dimensional inaccuracy comes? So it happens because of the uh, property of the material of basically thermal expansion and contraction. So it suppose for example we want to make a shaft something like this from a cutting tool like this. Okay, so let's say initially we have 100 mm and final dimension which we want, that is 50 mm. And since if the cutting velocity is too high, then the temperature rise is too much. So if temperature rise is too much, then what will happen? Then what will happen? What if we just focus in this region? Here in this region, if temperature rise has taken place, let's say about 500 degrees Celsius, because of the thermal expansion, because of the thermal expansion, the material will expand. Okay, so since at this point the temperature is high and we are maintaining the tool and workpiece position such that the final we are expecting a final diameter of 50 mm. So but when our tool will move ahead and our material will cool down, what will happen? Basically contraction will takes place. So we are aiming for the 50 mm, but because of the contraction we will get, let's say, 49 mm. So because of the high thermal coefficient, the dimensional inaccuracy may come in the workpiece. So that is not required, or that is the detrimental, because the when we take this component for the assembly, it will not fit into the respective hole. And so what will happen? Because of dimensional inaccuracy, our component, it will it will become scrap. There is no use of the component. So that is the wastage of money and time. So dimensional inaccuracy is the uh, one of the detrimental effect on the workpiece because of the temperature rise. Another is the surface damage due to the oxidation. Surface damage due to oxidation. So what happens if temperature rise is too much? Then the oxidation tendency of the most of the metals becomes very high, and that will damage the properties of the surface. So basically, if we are expecting good ductility, or we are expecting uh, good strength, but the component which we will get, its surface property will get changed because some oxide layer has deposited, and that will have different properties than what we were looking for. So that is the another detrimental effect. And the one more detrimental effect is there, that is the induction of induction of tensile residual stresses. So because of high temperature rise and non-uniform cooling, so this type of tensile residual stress that can takes place near the surface of the workpiece, so which is not required at all, because tensile residual stress means reduced fatigue life. So the fatigue life of the component will become smaller and component will fail prematurely. So that is not desirable at all. So these are the some of the effect because of the temperature rise. Now let's come back to the answer of this question. So temperature rise in primary and secondary deformation zone is generally due to the, in the primary we know the temperature rise takes place because of the shear deformation. Shear deformation takes place because of the plastic, we are applying some load and material is getting plastically deformed in form of chips. So temperature rise in primary zone is because of the plastic deformation of the metal, and in secondary deformation zone already we have discussed because of the friction between tool and chip. So the correct answer for this is B. So the correct answer is B. But still, if any of you have any doubt, please feel free to ask me. Okay, it seems there is no doubt. So we will quickly move to the next question. But still, if you feel any difficulty or if you have any doubt, please stop me in between. Feel free to ask me your doubts. Okay. So we are moving to the next problem. Please read the problem, and first you can try it by yourself. You can give your response in the chat box. After that we will discuss it together. I have got response from the Hamid. I am waiting for others. Yeah, sure. So we will discuss it. We will discuss it. But whatever you feel, you can, whatever you think as from your knowledge, you can give your response. Anyway, we will discuss it logically. Okay. So please don't hesitate. Whatever, uh, whatever answer seems suitable according to your knowledge, you can give your response. Okay. We will discuss, and still, if you have any doubt, we can clarify. Okay. I am waiting for others. Okay, let's try to discuss it together, and probably after discussing, uh, you may find it easier to answer. Okay. So the question is, which of the following conditions produce continuous chips? So, if you remember, there were uh, different types of chips which might have discussed in the lectures. So one is the continuous chips, one is the segmented chips or serrated chips, and another is the discontinuous chips. And this question is little tricky, so let's try to discuss it one by one. So first, try to think when we can get what, or when we can get continuous chips and when we can get discontinuous chips. So let's try to see with a small diagram. Suppose we okay, I will. This is the tool. Okay, I should make a good picture. This is the tool. This is chip, workpiece, and this is the tool. Here, what is happening? Here, a layer of material is getting deformed plastically across the shear plane. Okay, and whatever material is getting deformed is coming out in the form of chips. So if our chip, if we want continuous chips or continuous chip is coming out, it means indirectly what we can say, the chip is not breaking. So chip is continuous means chip is not breaking. And in general, so from our existing knowledge, what we can say, anything will, when we can see fracture or breakage in a material, so it happens when our material becomes a little brittle. So the continuous chips comes when we machine some tactile material first of all. So continuous chips takes place in the case of tactile materials. And if we try to machine some brittle material, let's say cast iron or some more brittle material, if we try to machine brittle material, then we will not get continuous chips at all. The chips will automatically break after uh, after certain length. So that is because of the brittle nature of material. So the first thing, the chip, if material is ductile, then there is a probability of getting continuous chips, and if material is brittle, then we will get discontinuous chips. But even in the case of ductile material also, if we play with the tool geometry and the cutting parameters, that is depth of cut, cutting velocity, feed, if we play with these parameters, then there is also possibility of getting discontinuous chips or let's say serrated chips. So now I will try to show some videos to you. So let's try to see the first video. Anyone can please tell, is it visible? Can you watch the video? Whether video is visible to all of you? Any of you can respond in the chat box. Okay, please try to observe what is happening. Okay, for simplicity, I will explain you quickly. This is the tool. Okay, and yes, Uma Maheshwari, you are telling correct. It is the continuous chips. So this is the workpiece, and here we are, chip formation is happening. And roughly if you try to see, material is coming like this and it is going this way. Okay, so this is the tool, it is the rake face. And if you can identify, so what is this angle? This is nothing but rake angle, which is alpha. So that is rake angle. Okay, and this is your uncut chip thickness or T1. So by giving this much of it, I will play the video again, and after that I will play 3 more videos and you have to tell your observation. Okay, okay, so this is the first video and now we will move to the next video. Okay, okay, now we will see 2 more videos. Okay, and after this we will see the last video. So all of these videos has been taken by high speed camera. So uh, so here it has been slowed down. So what you have observed, any one of you, if you have observed something, then you can let me know. You can unmute yourself, you can tell, or you can write in the chat box some observation. Okay, so let me help you out. So in first video, if you see, he, in all cases we have ductile material, we are machining or we are performing the cutting operation on ductile material. On the same material we are uh, cutting with the help of tool. Yes, rake angle are different, and in the last video discontinuous chips. Yes, yes, all of you are correct, exactly. So so what we can say, in all 4 cases we are trying to cut a ductile material. The only change which we are doing, we are changing the rake angle of the tool. In the first case, if you see, the rake angle is something alpha, and if you know the convention, if our rake angle is in this direction, then it is called positive rake. Whereas if the rake angle is going somewhere in this direction, that is the here, then whatever angle it will make here, it will call negative rake. So in first case we have seen there is a some positive rake angle. So here there is some angle that angle is positive rake angle. But if we see in the case of second video, again we are getting continuous chips. But here what is the rake angle? It is almost zero. It is making 0 degree with the perpendicular to the cutting velocity. So here the rake angle becomes alpha becomes 0. But coming to the next, here what happens if you observe the rake angle? Now it is making some negative rake angle, let's say alpha. But the observation is here the chips which we are getting, it having some projections like that. That is called serrated chips or segmented chips. But still it is a continuous chips. But if we further reduce or if we further make the rake angle more negative, then what we have seen, the chip formation has become discontinuous, whereas earlier it was continuous. So if we make the rake angle more negative here, then our chips started becomes becoming discontinuous. So this is the observation from the experimental results. So coming to the first question, so which are following uh, conditions to produce the continuous chips? First one is the large rake angle. Large rake angle, it will better. Now we have to understand a convention also. Large rake angle means positive. If we have positive rake angle, then we will get continuous chips. But if we reduce the rake angle, or if we reduce, if the rake angle is negative, then the chances of getting continuous chips is less. So yes, the first one seems to be correct. And let's coming to the second one, lower uncut chip thickness. So before that, what I will try to, I was telling you that we get discontinuous chips when our chip material starts becoming brittle. So let's try to look at the equation. So if you remember the cutting force, if you try to write it down, then it was coming w t1 tau s cos lambda minus alpha divided by sin phi cos phi plus lambda minus alpha. And this is width of the chips. This is the uncut chip thickness, and lambda is the friction angle, and phi is the shear angle, and alpha is the rake angle. So this is the cutting force. Okay, so again we will draw the diagram and try to see whether the cutting force has some relation with the uh, brittleness or ductile nature of the material. So here this is the chip. Here we have tool, this is chip, this is the workpiece. This is the thickness of uncut chip thickness. And here tau s is the shear strength of the material. So if we we are removing the same uncut chip thickness, T1 thickness we are removing with the cutting tool, but we had many options. Either we can take a small rectangle, or we can take large positive rectangle, or we can take more negative uh, rectangle. So chip chip behavior become ductile to brittle. Basically, if if we are applying less force to cut the material, then what we are doing, we are removing the material or cutting the material with less force. It means less plastic deformation. And if we are applying large force, that means we are we are doing more plastic deformation. So if you see the equation of the cutting force, it depends on the shear strength of the material, which is constant, and uncut chip thickness of the material, that is up to us. We can increase the chip thick, we, we can control the uncut chip thickness, and it depends on the shear angle also. It depends on the friction angle. For given set of tool and workpiece material, the friction angle will be constant. So the the only thing which we can control, that is the alpha. It is the tool geometry that we can control. And next one is the uncut chip thickness. So cutting force will depends on the rake angle which we are going to give, and the uncut chip thickness which we are going to provide. So if we are applying less force to cut the material, it means less plastic deformation is taking place. And if we are applying large force to cut the material, it means we are doing more plastic deformation. And if you remember, if we deform the plas if we deform a material plastically, then it will become harder, stronger, or more brittle. So more plastic deformation means the chip will become more harder, more stronger, its strength will increase, and it will become less ductile. So more plastic deformation means more hardness, more strength, less ductile, or we can say more brittleness. Okay, so if we increase the cutting force, that means the chip which will get produced, it will have more brittle nature. And more brittleness means what? Discontinuous chips. Okay, so from the given equation, as I told, if you keep on increasing the rake angle, or you keep on increasing the positive value of alpha, then the fc value will comes down. So if you increase the alpha, fc will come down. It means more ductile. It means chip will become continuous. Okay. And if you see that, if we keep on increasing the uncut chip thickness, if we increase the uncut chip thickness, definitely we have to give more force to deform the material, and we will deform the material plastically, and also that will also make us the that will also may change the continuous chips to the discontinuous chips. So more T1 means, again, force fc will increase, and that will cause discontinuous chips. So if we see the problem, so we have seen larger positive rake angle means less cutting force, continuous chips. Again, lower uncut chip thickness, less cutting force, continuous chips. And the last one is the cutting with the cutting fluid. Yes, again, if we decrease the friction between the chip tool interface, again we have to apply less force, and our if the friction value is less in between the tool rake face and the chip, then chip can flow smoothly over the rake face, and it will retain its continuous behavior. So if we use the cutting fluid rather than dry cutting, then also the chip nature which we can expect from a ductile material is continuous. So all three options are correct. So in order to produce continuous chips, all three options are correct. So final answer for this question is the D, all of these. So correct answer is D. If any of you have any doubt, please ask me. So in this equation, for cutting force equation, one assumption which we have taken, that the shear angle, that phi, is doesn't get affected much if we are changing the rake angle. So assumption phi is more or less constant if even if we change the rake angle. Phi is not affected by, not much by alpha. So yes, I have explained the answer of this question, but still any of you have any doubt, please ask me. Just remember one thing: continuous chip is, it has it is more probable when we have ductile material. But somehow if we are changing the ductile nature from ductile to brittleness, then it is more expected to get the discontinuous chips. So that can be done by many ways. Okay, is it clear to everyone? Any of you any of you have any doubt? Okay, we will move to the next problem then. Please read the problem, and then we will discuss it together. Okay, you can give your response in the chat box. I am waiting for others. Okay, so let me quickly help you out. So, built a page is produced at. So, before that, I will quickly try to explain what is the built a page. So, okay, we'll quickly draw the diagram. Okay, so we have a workpiece and we are trying to cut it with the tool. Okay, so there is cutting velocity which is given to the workpiece, that is V. This is tool, this is chip, this is workpiece, and here we have a rake face. So when we cut the ductile materials, what happens? I told that there is a tendency of ductile material to form continuous chips. And what is happening here? What is happening here? If we just focus the tool tip, so material it is coming here, and here we have a shear plane, and after and it is getting deformed across the shear plane. So and this is the primary deformation zone. Okay, so if you just focus the region here near the tool tip, what is happening? Suppose if some material is here, say blue, it is in blue color, the material which is very close to the tool tip, it is experiencing a large compressive force. So how? First it is getting compression force from here, here, from top side also, and here from tool is also providing another force. So it is facing almost all sided compression force the material near the tool tip. So if material is ductile, if it is ductile, then continuous chip formation is will keep on taking place. If continuous chip formation is taking place, then what happened to the temperature near the tool tip? Definitely it will increase too much, so temperature rise will take place. So because of continuous contact of chip and tool, the temperature rise will takes place because of generation of continuous generation of heat, and which is not getting dissipated very quickly. So temperature rise will take place, and because of rise in temperature, what will happen? Then then there is a chance where, because of temperature rise, the sticking of workpiece material to tool rake face or the tool tips will happen. Because of temperature rise, there is tendency of the material of adhering addition So there is a tendency of material near the tool tip to get adhered at the rake face. So addition of workpiece material at tool tip. So when we are machining ductile material, there is continuous chip tool contact at high velocity, and because of that temperature rise will take place, and because of temperature rise addition of workpiece material at tool tip will take place. And sometime what happens, the because of addition, this metal, the workpiece material, if it has good affinity with the tool, then it will gets welded to the tool locally. So so it is adhered, or we can say it gets welded. And now, earlier our tool geometry was like this, okay, but when some small chunk of material get adhered to the tool, then what will happen? Our tool geometry will become something like this, okay. Then now the adhered material itself become a part of the tool, and now cutting will happen from this edge, from here. Earlier the cutting was happening because of the sharp edge of the tool, but now because of this addition of this small chunk of material, the cutting process has been taking place by this small portion of sticked material, and this is not that much sharp, it is blunt. And if after some time, because of force which is up keep on applying to the to this region, because of continuous force, after some time this will get carried away, this will break down, and some portion of will comes towards the workpiece, and some portion is taken away by the chips. So this small chunk of material which has formed here due to the addition process, that is called the built up edge. Built up edge. This is not desirable at all. So why it is not desirable? First thing, when it breaks, when the built up edge gets break, some portion of it comes to the finished surface of the workpiece, and which deteriorates the surface finish of the workpiece. So built up is it surface finish is reduces the it reduces the surface finish. Surface finish goes down, as well as it is forming, and it is breaking, forming, breaking, forming, breaking. Because of this process, there is a large fluctuation of load takes place. Large fluctuation of load takes place, and because of this, vibration comes during the machining, which is not desirable. Undesired vibrations occurs. And also, because of built up base, it sometime it all the bonding between tool and built up base becomes very strong, but when it gets detached, so it takes away some chunk of material from the tool. So indirectly we can say it increases the tool wear. So what we can say, we can say that at built up age, it's a very undesirable phenomena which take place during the cutting of ductile material. So this is not desirable. But again, if we try to see what has been asked in the question, so first one is a large rake angle. So I told that uh, the buildup has formed because of sticking of material near the tool tip. But I told that if we have large positive rake angle, if we have large positive rake angle, then there will be less cutting force, and if there is less cutting force, then less temperature rise will takes place. So if large rake angle will be there, then the cutting force which is required, will be less, and the temperature rise will become smaller. And if temperature rise will smaller, then there is the formation tendency of built up edge will become smaller. So large rake angle will reduce the formation of cutting edge. If large angle will reduce the formation of cutting edge, indirectly we can say low angle will increase the tendency of formation of cutting edge. And option B is the lower uncut chip thickness. If uncut chip thickness is lower, then cutting force will also be lower. If cutting force is lower, then temperature rise will also lower, and built up edge formation will suppressed. So lower uncut chipness doesn't promotes the built up edge. So the correct option is low rake angle. So is it clear to everyone? If any of you have any doubt, please ask me. Okay, it seems there is no doubt, so we will move to the next problem. And later on, if you feel any problem, you can ask me. Okay, please read the problem and try to solve it by yourself. You can keep your response in the chat box. After that, we will discuss it together. Okay, I have got response from Hamid. So others, I'm waiting for others. Okay, Srinivas has given second option B. Okay, so let's try to see together. Okay, so what has been asked in the question: if the cutting speed is doubled, then what will be the effect of tool life according to the Taylor's tool life equation where n value is given? So Taylor's tool life equation, we need to write it down. Taylor's tool life equation. So that is given by v t to the power n is equals to some constant, where v is the cutting velocity and t is the tool life. N and c are the constant that is depends upon the uh, tool workpiece material. So what is given here? So here it has been asked, if cutting speed is doubled, if we are doubling the cutting speed, then what effect we are going to feel on the tool life? So here n value is given 0.596. So let's we have velocity v1, and corresponding to velocity v1 we have the tool life, let's say t1. Okay, so if we want to write Taylor's equation for the initial cutting velocity, so what we will write, v1 t1 to the power n is equals to c. But if we increase the tool life, then in that case what we can say, sorry, if we increase the cutting velocity v2, that will be 2 times of v1. And if we want to write the Taylor's tool life equation for the second case, where we have increased the cutting velocity and all other things are same, so what we will write, v2 t to the power n is equals to constant. Now we know v2 is double of v1, then what we can write, 2v1 t to the power n is equals to constant. Now we can equate, let's say, equation 1 and equation 2, because right side is RHS is equal. So what we can write, v1 t1, and we can substitute n also. N is 0.596. v1 t1 to the power 0.596 is equal to 2v1 t to the power 0.596. And if you rearrange this equation, what you will get, t2 by t1 is equals to v1 divided by 2 times of v1 raised to the power 1 upon 0.596. And if you try to calculate t2 in the terms of t1, you will get t2 equals to 0.3125 of t1, or t2 equals to 5 by 16 times of t1. So what will be the correct answer? B. Okay, so any of you have any doubt in this question? Is it clear to everyone? Okay, it seems it is clear to everyone, so we will move to the next problem. Please read the problem, and you can keep your response in the chat box. I have got response from the Nagasil Nimas. I am waiting for others. Okay, so let's try to see together which, which of following is not an example of solid state welding. So please note down here a note is there. So first of all we need to understand what is the solid state welding. So yes, Amit, yes, correct. So you need to keep the answer which is not an example of solid state welding. Okay, so uh, we are discussing here like what is the solid state welding. So the main motive of the welding process is to join two components together. So there are many ways to join. So you already have seen many places. If you want to join two metals, what we do, we increase its temperature and locally we melt the material, and then we bring them together and we leave it to solidify for some time, and then they will get jointed. So here we jointed the metal by melting it. So in melting we know the material changes its phase from solid to liquid. So that is the liquid state welding. And in solid state welding, we are trying to join the material without entering into the molten phase. So let's try to see the different processes. So first one is the diffusion process. So what happens, uh, if you see, suppose if you have a block of metal, so what, if you visualize what is there inside the metal, there is some positive charge nucleus inside the material. It is made up of atoms, and all atoms have a positive nucleus, and there is it is surrounded by sea of electrons. Okay, so if we see a solid block of metal, so the solid block is held together by the electrostatic forces between the electron and the nucleus of the material. Similarly, if we have another solid block, there also we have some positive charge nucleus, and that is surrounded by electrons. So these two blocks are independently held together by the atomic forces or the or the electrostatic forces or the nuclear forces. So these are held together by themselves. But somehow, just imagine, somehow if we bring these two surfaces together, then what will happen? So if we bring them sufficiently close, then the electrons from block 1, let's say 1 and 2 electrons from block 1, they will get attracted by the nucleus of the block 2, and the electrons of block 2, mm, they will get attracted by the nucleus of block 1. So if they bought a very close distance, then this kind of process will happen, and they will, after some time, what will happen, they will join together, and ultimately they will become a single object. So that is that kind of phenomena where the electrons of from one material will get entered to the second material and vice versa. This kind of process will take place in some conditions. So those conditions are, first thing, those the contacting phase or the flying surfaces, they should come very close. And another thing is, for the moment for the accelerated movement of atoms and electrons from one body to another body, we have to increase the temperature. So so if we increase the temperature and we will bring both surfaces together, then there is this possibility of uh, both material will get joined, and atoms and electrons from one material will go into each other and they will become single body, and that process is called diffusion. So diffusion is nothing, it is but it is the moment of atoms or charged particles from one location to another location because of virtue of concentration gradient, and that can be done only at elevated temperatures. So this kind of process is also used for joining two metals. So in order to bring them together, we apply a large force so that both surfaces comes closer, and same time we increase the temperature also so that the atomic exchange because of diffusion becomes faster and they will get jointed. That is called the diffusion bonding. And next process is the friction welding. So in friction welding, what we do, we have two parts here and we want to join them. But what happens, one of the part is rotating, and what we do, we bring this second part closer to the first part which is rotating, and we apply some pressure from the both side, and because and they will contact to each other, and because of friction the heat will generated, and because of generation of heat as well as the pressure, the material gets plastically deformed and they will adhere to each other, and this process is called the friction welding. Here also we are generating the heat as well as we are deforming the material plastically, so that the this kind of situation we can bring here also. We are bringing the both material together, both surfaces together, and we are deforming it plastically so that the contact between them gets established, and here heat is generating because of friction, and because of the rise in temperature and plastic deformation the material gets joined. So that is called the friction welding process. And the third one is the cold welding. It is very similar to the friction welding. The only difference is here the both materials, we had this workpiece material and they are brought together with the help of dies. So here we have dies which guides them to come together, and again some they are given some plastic deformation and some temperature rise. We also provide some temperature rise, and again plastic deformation and temperature rise will cause the materials to join together. So that is the cold welding. So it is very similar to the friction welding. The only difference is the here the material is getting guided by the with the help of dies. And the last one is the thermite welding. So in thermite welding, uh, the what we do, we we had some chemical components, and we try to do some chemical reaction because of which heats get generated, and the material, the we have some filler material which gets melted with the help of chemical reactions, and we pour this filler material in between the gaps where we want to join. So ultimately what we are doing, we are melting the filler material and we are putting it inside the in the gaps between two materials to be joined, and finally it gets wilted. And the chemical components which uh, the chemical components because of which reaction takes place, that is called thermite. And here the since liquid, here we are forming the liquid, therefore this kind of process is comes under the liquid state joining process. So thermite, so except the thermite welding, all others are examples of solid state welding. So correct option for this is thermite welding. So here I have given a YouTube link. You can go and you can watch the animated process of the thermite welding. So uh, right now I am running out of time. So if time permits, I will show you. Otherwise, later on you can find it on the YouTube. So yes, correct answer is D. So any of you have any doubt? Okay. So let's move to the next problem. Please read the problem and try to give your response in the chat box. After that, we will discuss it together. Yes, I have got the mixed response from all of you. Okay, so let's quickly discuss this problem. So, which of following is not an important factor in solid phase welding? So, just I will take an example, and from there we will try to figure out what is the correct answer. Okay, so I told that. Okay, okay, Maheshwari. Okay, uh, we will figure it out. What is the correct answer? So in okay, so in solid phase joining or solid phase welding, what we have seen, we had two objects, like we have two surfaces, and we want to join them together without melting it. Okay, so for that, what I told, if we apply some load on these two material, and same time if we increase the temperature, then then both surfaces will comes in contact, they will come closer, and there is metallic continuity takes place, and there is a bond formation will takes place. Okay, I need to see the chat box. I think the type of bonding and recrystallization are important factors in solid phase welding. Okay, okay, I think probably discussing after my discussion it will become clear what are important factors, what are not. So okay, so let's discuss with me, and after that you can ask if you have any doubt. Okay, so we want to join these two surfaces without melting them. So if you if you see microscopically what is there, do you think any material is perfectly flat or perfectly smooth? No, they are not perfectly flat nor perfectly smooth. Basically, if you see microscopically, these type of peaks and valleys are there at different locations of the surface. Okay, and if you just try to bring them together, then what probably you will see? You will find some contact of this type. I am exaggerating. So I am zooming it out. I am zooming this region. Let's say here. So so you try to bring both surface together, but right now you haven't applied any load. So what you will see, you will means you will think, yes, since I am brought to both surfaces together, so they might come, they might have there might be a perfect contact between them, but in fact it is not there. There only some peaks to peaks contacts takes place. And I told you, in order to make, if you want to join these two materials together, what should happen? The electrons and atoms, they should form a permanent bond. So this can happen only when these two surfaces comes in close contact. Right now, the that kind of region is very less. Right now, we haven't applied any load. Just we had brought them together by hand. So in that case, only very small contact area will be established, and these are very small, so that they are not sufficient for the permanent bonding between these two surfaces. So what will happen when we apply some load? When we apply some load, then what will happen? Both materials will get plastically deformed, something like this. Or I will draw again. So right now, earlier only peak to peak contact was there, only point contact was there between the two surfaces. But right now, if you, I will again exaggerate. Some surface contact will takes place, something like this. Okay, now at least we have got some reasons where some area where the electrons and nucleus of both material they came in the contact. Okay, so why this has happened? This has happened because of we applied some load, and because of load these these pointed material gets deformed plastically, and because of that we have got some surface contact area. So one thing we can say, surface deformation or plastic deformation of the asperities, that is responsible or that plays important role in the solid phase bonding building. So one is that is the one of the important factor. And same time I also told, if you want to increase the rate of diffusion or the rate of transfer of atoms from one material to another so that they will become single entity, then you have to increase the temperature. So if you want joining process to become faster, you will increase the temperature, and because of which the rate of diffusion will increase, and we will get the joining process will become faster. So we are also increasing the temperature, but we have to one thing I want to tell, normally if the Tm is the melting point of material, then diffusion process effectively takes place above the zero point 0.5 of melting point. If temperature is higher than zero point 0.5 of melting point, then diffusion process happens at very high rate so that we could reduce our the joining time. But same time, if you remember, the recrystallization temperature of any material is also, normally it is, if recrystallization temperature, it is also if so zero point 0.3 of Tm. So what happens if we increase the temperature above the zero point 0.3 of melting temperature, or let's say if you are increasing the temperature 0.5 of melting temperature, then the grains in this region, they will start recrystallizing. So like earlier the grains was like that, or I shall make some fresh diagram for better understanding. Suppose I am zooming this portion here. So these are the grain boundaries in the material. Okay, so this was at the room temperature, but now since we wanted to join them, we want to increase the diffusion process faster, we increase the temperature, and since temperature has been increased, the grains starts recrystallizing. So what can happen, there is one possibility that grain size becomes larger because of recrystallization. So if this will happen, then what will happen to the strength of the welding? Definitely, the if we increase the grain size, then the strength of material decreases, or we can say ductility of material increases. So because of temperature, recrystallization process taken place, and that changes the strength of the welding. So we can say recrystallization also affects the solid state welding, or recrystallization affects the strength of the weld in the solid state. Now coming to the surface films. If you you must be knowing, if we have any material in the atmosphere, suppose aluminum, iron, whatever you can think of, they are not, if you see the surface, they are not pure material. Because of oxidation, they form oxide layer on their surface. Okay, so there is a oxide layer present on all kinds of metal. So if we want join these two metals with oxide layer, we will not able to join them. We are able to make the bonds between, let's say we have aluminum. So if aluminum atoms will comes in the contact of aluminum, then only they will form a bond. So if we want join them by solid state joining, what we do, we clean the surface, we remove the oxide layer, and then we will apply some pressure on the cleaned surface, and then we increase the temperature, then they will get joined. So presence of surface films, it will reduce, or I can say they will restrict the welding of solid phase welding. So this is this will affect the solid state welding process. So now coming to the type of bonding, so that has nothing to do with the solid state welding process. We know the, if we want to join the two metals, then they can be joined only with the help of metallurgical bonding. So that will not play, and that cannot be changed, and that we cannot control type of bonding. So we can control surface deformation by applying load. We can avoid recrystallization by controlling temperature, and we can remove, or we can control the surface film by cleaning the surface. So the correct answer for this is the type of bonding. So any of you have any doubt? Is it clear? Okay. Okay, if there is no doubt, then probably we can discuss one last question, and then it will be all for the today. Please read the problem, and at least you can think of how to approach this problem. So this question is all about the arc welding process. So uh, here it is given a direct current welding machine with a linear power source. Characteristics provide open circuit voltage of 80 volts and short circuit current of 800 amperes. During welding the machine, the measured arc current is 500 ampere, corresponding to the arc length of 5 mm, and the measured arc current is for 60 ampere, corresponding to arc length of 7 mm. The linear voltage arc length characteristics of the welding can be given as, so we have to find out a relation between the voltage and length of the arc. So that is the problem, and we have given some conditions, and we need to find out the linear voltage and arc length. We have to find a relationship. Can you think of and if any one of you have any clue how to do that, you can unmute yourself, you can tell me, or you can write in the chat box. And briefly you can write 1 or 2 lines if if you have any idea how to solve this question, how to get the relationship between the voltage and the arc length by given information. Okay, okay, I will quickly help you out, and later on you can go to your home and you can try, and you can again try it by yourself. Okay, so first thing, I will quickly talk about the arc welding process. So in arc welding, what we do, we have, so basically we have two materials which we want to join them here. We bring them together, and we have an electrode, and we apply some voltage. Normally we apply positive positive for positive volt to the workpiece, and we apply some negative potential to the electrode, and this we call anode, and this electrode we call it cathode. And our aim is to join these two metals, let's say 1 and 2, and same time we try to fill this gap with the by melting the cathode material. And usually the cathode material is also same as the parent metal or the base metal, that is 1 and 2. So if we apply a higher voltage between anode and cathode, then the current, basically, if you have seen the welding process, what we do initially, we bring the cathode, okay, Sandeep Kashyap, in this question A and C, but the important option in these question A and C, but the important factor C are given. Option B and C is given. Actually, Sandeep, I will not able to understand what is written. Okay, so this is, I cannot understand, Sandeep. It will be better if you can unmute yourself. You can tell me. I am not able to understand, or you can discuss after this problem. Okay, if you have any doubt, we can discuss after discussing this problem. Okay, I was telling that we are trying to join these two materials with the help of some filler material that is called cathode, and we have applied some potential difference between the cathode and anode. So initially what we do, we bring the cathode in the contact of the anode material, and since there is potential difference between these two, there is current flow will start taking place from uh, let's say electron starts flowing from cathode to anode, and current will start flowing from anode to cathode. And simultaneously what we do, we are trying to separate the cathode and anode. In the current is running and we are trying to separate cathode and anode, and there is a big there is a huge current which is running between anode and cathode, and because of that the temperature rise has taken place in this region. And when we separate out, because of high temperature, the both of because of the high temperature, the thermionic emissions of electron starts taking place. So if you recollect that if we apply high temperature and we apply high potential between the two conducting materials, then after crossing the work function of the material, if we given sufficient energy, then electrons starts emitting from a surface, and because of potential, electrons will accelerate, and this process will create arc or plasma. So plasma is nothing. So in between these, when we separate out these two materials and electrons are moving, these electrons will strike to the air particles which is between these two materials, and electron will come and it will hit the air particle and it will ionize it, and the ionized form of air and it is mixed with the electrons, that is called plasma. So a region of plasma get established in this region, which we can see in the form of arc. So that is the process of formation of arc. And same time current is keep on flowing. Current is keep on flowing in the form of plasma in this region, and there is, we know, when current moves from one location to another location, there is drop of potential takes place based on the resistance to movement of electrons. So this is the profile. If you see the arc, there are five main regions in the arc. One is the cathode spot. So cathode spot is nothing from where the electrons are generating. So that is the cathode spot. And after that, there is a small region. Since this cathode is negatively charged, So it is negative charge, therefore it is surrounded by some positive ions, and this small region of positive ions, that is called cathode space. Cathode space. Cathode space. And after that, a long region comes, that is called arc column. This is arc column. And here where the electrons are striking, that is called anode spot. Anode spot. And it, since it is positively charged, so the area surrounding it is, there is a region where it is surrounded by, there is nearby region it is surrounded by electrons, that is called anode drop. Okay, so I was telling the electrons are moving from cathode to anode, like here. So they are traveling. So based on the resistance, the potential drop takes place. So here I am showing the potential drop or voltage. So when electrons move from cathode spot to the cathode drop region, there is a huge potential drop takes place. And when it travels inside the arc column, then only a small amount of, this much amount of potential drop takes place for a long region. And after that also there is a sudden drop of potential takes place. So this is the main reason of, main region of the arc, and that is the linear curve between the arc length and potential drop. And we have to find out this relationship. What is the equation of this line? Okay, so for that, first information which is given, that is for the power source. So let's write it down. So from power source characteristics, if you see the question, what is given? Linear power source characteristics. Okay, so it is given linear. So what we can write, there is some relation between current and voltage. So that is linear relationship, that is we can write a plus bi, or I should write capital I, some 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 this kind of relation will be there, because power source is linear. So what is given? Open circuit voltage is given. Open circuit voltage, that is 80 volts. And we know open circuit means what? Open circuit means current is zero. So when current is zero, at that point of time, the potential difference between the two electrodes of the power source, that is 80 volts. And what else is given? Short circuit current. Short circuit current, that is given 800 amperes. And what we know, when we say short circuit, it means high amount of current is flowing, or we can say there is no resistance in the path of the uh, current. There is no resistance for the electrons, so voltage drop will be zero. So open circuit means current is zero, short circuit means voltage drop is zero. So now from these two information, we will try to find out this equation. What we have to find out? We have to find out A and B. So from the first equation, if we put I is equal to 0, we will get V is equals to A, or V is given 80 volts is equals to A. So A is 80 volts. Similarly, if we put the second condition, we will put voltage equals to 0. So if we put voltage equals to 0, we will get this kind of relationship, or we can say I is equals to minus A by B. And already we have calculated the value of A. So, and it is given the short circuit current is 800 amperes. From there we can calculate B. So B will comes out 1 by 10. And if substitute A and B, the linear relationship which we will get from the power source, that is V equals to 80 minus I upon 10. So this is the equation which governs the characteristics of our power source. But what has been asked in the question, it has been asked, we have to find out a relationship between voltage and length of arc. For that we have given some conditions. So if you see in the arc region, there is a linear relationship. It is linear. There is a linear relationship between the arc length and voltage. Then from now we will write same kind of equation for the arc, voltage characteristics. So from arc voltage characteristics, what we can write? We can write a linear equation between voltage and length of arc. So we can write V is equals to some another constant A plus some other constant B times length of arc. Now what else we have given? We have been given here the information regarding the arc. It has been given when the arc length was 5 centimeter. When arc length was 5 centimeter, at that time the current of the arc was 500 amperes. And when we increase the length of arc to 7 mm, then its current value has been increased to 460 amperes. So basically what we can say, we have given two boundary conditions for this equation that we will write it down. At arc length of L is equals to 5 mm, the current value was 500 amperes. Okay, so what we can write, but so this is the voltage drop. We have written it down for the arc, and sorry, arc, and already we have found out a voltage relationship, voltage and current relationship from the power source characteristics. And here we have written a relationship between voltage and arc length, but boundary condition which we have been given, that is between the length and current. So we have to find out a relationship between the arc length and current. So from this equation, or we can write it equation 2, and we can write it equation 1, we can equate the voltage, and from there we can get the relationship between the current I and the length L. Okay, so if we substitute the voltage from equation 1 into equation 2, what we will get, A plus PL is equals to 80 minus I by 10. Okay, now from the first condition here, we will put L is equal to 5 mm and I is equal to 500 amperes. What we will get A plus 5P is equals to 80 minus we will get A plus P is equals to 80 minus I by I is 500 by 10. And similarly again, at arc length L is equals to 7 mm, what is given, I is equals to 460 amperes. We will put the L is equal to 7 and I is equal to 460. So what we will get, A plus 7B is equals to 80 minus 460 by 10. So finally we will get equation 3 and equation 4, and we have two unknowns, A and B. And when we solve it out, finally, if you solve it out, then final answer which we will get, that I will write it here. You solve it out, you can find it out. B is equals to 2 and A is equals to 20. So now we have find out value of A and B. We will substitute this value here, and we will get the relationship between voltage and arc length. So what we will get, V is equals to 20 plus 2L. So the correct answer for this problem is C. Okay, so is it clear to everyone? Any of you have any doubt? Okay, you can keep your response in the chat box if it is. Okay, Hamid, we will go to the last slide. Yes. Okay, how you get p value, Naga Srinivas? Okay, so Srinivas, here up to this, is it clear how we have written this equation? So this equation, yes, okay. So in this equation, what we are looking for, we are trying to find out a relationship between voltage and arc length. Okay, and this voltage is nothing, it is same as this voltage. Okay, so now I substituted that v with this this value, I minus I by 10. So 80 minus I by 10, this equation I have substituted here. And if you substitute this equation, this thing came here, and this v becomes this. Okay, now what we are there?
Okay, sir.
Okay, is it clear?
Sir, my doubt is how we get that p value 1/10.
Yeah, here.
Previously, previous
Okay,
slide,
correct, correct.
b
Can
is
you see
equal to
here?
1/10.
Okay, from, see, this equation, what it shows? It shows a relationship between voltage and current. Okay, that is given for the, that if you see in the question, it is given a linear power source. For linear power
Okay, sir.
source mean we have this kind of relation. There is a linear relationship between voltage and current, but we don't know A and B. But we have given two information. One is the open circuit voltage 80 volt, and we have given short circuit current 800 amperes.
Okay, sir.
Okay, so it,
Uh,
if we put 80 volts at that point of time, current will become zero, because that is open circuit voltage. Okay, open
okay,
circuit
sir.
voltage means no current is flowing in the circuit.
Yes, sir.
So if we put I is equals to 0, and voltage value 80, so if you put I 0, it means this relationship will come. Directly we will
Okay.
get A is equal to 80 volts.
Yes, sir.
Now from the second relationship, short circuit current, that is 800 ampere, and short
Okay, sir.
circuit current means voltage is 0. So if you put voltage 0 and current value 800 amperes,
Okay.
and we already, you will get this kind of relationship. Okay,
Yes, sir.
and A already we know, that is 80 ampere.
8
Okay, and current, 800 amperes I.
Okay.
Okay, or
Yes,
we can
sir.
say B is equals to minus, uh, uh, that what we have to
b
find
is
out, we
equal to
can,
80 by 800, I think.
yeah. So you got it, na?
Yes, sir.
Okay,
80 by
okay,
100,
yeah,
800.
yeah, okay, so,
Okay, right, sir.
okay, so someone has doubt in this question. Okay, which one of following is an important factor in surface deformation, type of bonding, recrystallization, both B and C? So this question is all about, we have to find out a factor which is not important in the case of solid state joining. Okay, so one by one, already we have discussed how surface deformation is responsible for the strength of bond which we get during the welding. So surface, I told that if you closely look at the surface, there is only point contact between the surfaces, between the peaks. But when you apply some load, then these points gets deformed, and it, so this peak will get converted something like this because of plastic deformation. So material which is here, it will flow here, it will flow here, and it will finally deform something like this. Now, because of this plastic deformation, the earlier we had point contact. Point contact, there is, because in point contact the bonding will not happen sufficient. But if we have area contact, then there is a good there is a there is a good bonding, or the bonding region or metallurgical metallic continuity region will increase, and that is responsible for the bonding or the solid state welding. So if the surface deformation is more or the deformation is higher, then the bond we will get for after the solid state bonding, that will have high strength. So surface deformation has important role in the strength of the welding, solid state welding. So that is correct. And for the recrystallization, I told, if temperature is high, then the grain size may alter, and because of that, again the strength of bond will get affected. If the grain size become coarser, then bond become the in material will become more ductile. And the if after recrystallization the size of grains will become smaller, then the strength of weld will increase. So recrystallization of grains is going to change the size of the grains in the bonding region, and that will affect the strength of the welded portion. And for the surface films, oxide layer, if we don't remove oxide layer, then whatever we will do, we will not able to bond them by solid state bonding. So we have to remove, we clean the surface so that we could get the metal to metal contact. Metal will join to the metal only, it will not join to the oxide. So whatever oxide is present, we need to clean it off. So here, in, if suppose this is the oxide layer, we will clean it by rubbing, by polishing, by scratching. So there are many methods. We will remove the oxide layer, we will then we will bring them together, then only they will there is possibility of metal to metal contact, and there is possibility of formation of metallic bond between the material. So surface films, this we have to remove. So the amount of surface film which is present on the metal surface, that is also going to play important role in the solid state welding. So these three are responsible, and these three things which we can control. And the type of bonding, this is not our control. And type of bonding, if we talk about metal to metal, the only possibility they can be joined, that is metallurgical bond, and that is beyond our control. We cannot change that type of bond. Therefore the correct answer for this is A. The option A, the type of bonding, it is not an important factor for the solid state welding, or we cannot control. We don't have any control on the type of bonding. So that's why option A is correct. Is it clear now, Sandeep? Sandeep, are you here? Sandeep, can you listen me? Am I audible to others? Hello.
Yes, sir.
Yeah. So actually, I was okay. I was answering to the Sandeep's doubt. Sandeep, now it's clear, or still you have some doubt? I have repeated the solution of this problem number 7. Sandeep, Sandeep, am I clear? Okay. Okay. Apart from Sandeep, anyone else have any doubt? So is it clear to everyone? So okay. So today I want to discuss only up to here. In next class, we will discuss some new problems based on the video lectures of the week 7. So till now, if it is clear, then we can end the session here. So if you have any query, any doubt, please feel free to ask me. And if you want to give any feedback, any suggestions, so you are welcome. Okay. So if it is clear to everyone, so we will end this session here and we will meet next Tuesday uh, at the same timing at 6 p.m. Okay. Okay. Then good night. Happy Holi. Bye bye everyone. We'll meet in the next week. Okay. Okay. Okay, Hamid, you can also download this PPT from the NPTEL website, but I can also, I will share my email to you. Okay, okay, I have got your email, so I will also find it out. I will also send uh, a copy of this PDF, and you can also find the earlier you can find out the copy of earlier presentations on the NPTEL website. So for this week, I will send you this one. And still, if any of you have any doubt, so I have shared my email. So uh, you can, please feel free to ask any doubt. Okay. Okay. So if there is no doubt, there is no suggestions, then I will end the session here. Okay. Bye. Good night.